Hello, my name is John Butler and I'm a lecturer in the School of Mathematical Sciences in TU Dublin. And I'm going to talk a bit about my experiences using data analytics, mathematics and statistics, and how it has actually helped me bridge between robotics, neuroscience, medicine, and also I'm going to touch a bit upon pandemics as well. So just a bit about myself. I did a PhD in numerical analysis, which is a form of computational fluid. So I was a computer mathematician. After that, I went to Germany, to the Max Planck Institute, where I did something very different. And this is where the robotics came in. I started actually, robotics and neuroscience, I started studying people and how people move. So self-motion, so how we drive, how we walk, how we run, how we cycle. And then from that, I moved to America, to the Albert Einstein College of Medicine, and I started looking at how the brain, and specifically brainwaves, are in different developmental disorders like autism or Niemann-Pick or Rett's, or also in typically developing, but also in adults as well. So once again, very different from computational mathematics, but you'll see how it all links, hopefully. And then I came back to Ireland and I started working on movement disorders. This includes Parkinson's, which I'll talk about at the end, and dystonia as well. More recently, in TU Dublin, I work with an optometry group who are investigating short-sightedness and also the impact of diabetes on myopia or short-sightedness. And my own work is computational neuroscience, where I make models to hopefully describe how the brain works. And these models will help inform treatments, but also make us understand of actually what's happening to people. So the first thing is self-motion. So I'm going to tell you a bit about what I mean by self-motion. And then why did I need virtual reality, and how, once again, maths and stats and data analysis came in. Then I'm going to talk about a series of studies where I record the brain, and this required a lot of data analysis and a lot of statistics to really interpret. More recently, I started building models, so mathematical models to describe and predict what happens in the brain and how the brain changes over time and due to disease. And also, I'll show that actually the mathematics of the brain is very similar to mathematics pandemics, and is also very similar to mathematics to describing how populations interact, which is really what pandemics are. So, first, how does a mathematician, or how does a statistician, or how does a data person look at the world? Specifically, how would I look at the brain? And so I have an input, and that's sensory, and I'll talk about that in a minute. The brain is the thing we don't know anything about. And then we have the output. And this is how you think about statistics. Is I have some information. I know what the end is. So I want to find out what happens in the middle part, in the brain part. And that's what you do. That's why I need statistics, data analytics, and mathematics. Different tools can explain different ways we interact with the world, different ways we think, but also, once again, I'm talking about sensory, but this is the same thing as our input could be, for example, a pandemic. Our output is our population, and we're interested in how the pandemic operates on it. Yeah. So you have to think about this. There's some function that describes how we interact. So what is self-motion? I said this earlier. Self-motion is walking and driving. You're going to, well, we all understand how that works, but we really don't. And the reason why this is so important is one of the leading causes for reduction in quality of life is falls in the elderly. It doesn't matter if you have a condition, be it Parkinson's, which affects your walking, or Alzheimer's, which affects your motor function. Even if you're a healthy older person, if you fall, your life expectancy is reduced immediately. Your quality of life is reduced immediately. It is essential to understand actually how we walk, how our brain does this. And so I talk about cue integration, but what I mean is, as we walk, we take in different things. We take in what we see, but also we take in what we feel. And so that's actually, a lot of my work was actually not on the vision part, was on the body part. And you all think, most people think the body parts are just our legs. But actually, there's a little thing beside our ear inner ear called the vestibular system. And that's so important because that actually is recording as good as your phone right now. You know, when you tilt your phone, it knows to change the screen. That exact same mechanism is actually in your head. So when you tilt your head left and right, your eyes rotate. When you move your head left and right, your eyes go the opposite way, just the same thing. So this is essential, and it's also very important for self-motion. And the other part is the one, maybe you don't know the word proprioception or somatosensory, but that's the one we're more used to. That's our joints, that's our feeling when we're moving, but these are very important. These are actually more important than vision. These are the feedback we care about. So I wanted to study this, and that's why I had to use virtuality. So I started studying this back in 2008, 2009, 2006, actually, sorry. And back then, virtuality was quite new. What you see there is an image of someone walking on a treadmill, and they're wearing a head-mounted display, and we're doing the body tracking. That's become very common now. Back then, it was quite rare. On the right, that's actually a robot. It's not the classic-looking robot. What is? It's called a motion platform. It moves up and down and moves around, so you can control it precisely. So I had to learn robotics. As my time went on in Germany, they got a much bigger robot, and this is it. This was known as the RoboCoaster. It was initially designed to lift cars, but the head of the lab I was working in saw it one day and said, you know what, that'd be really good at? Lifting people. And so we were able to look at the mathematics of the movement of it to get precise movement, to actually recreate exactly how someone moves when they drive. So we were able to make a helicopter simulator and a driving simulator that could actually reproduce full movement. Because right now, a lot of the simulators are, you just see the vision, and that's fine, it works quite well. But in reality, when you're flying or when you're driving, you want to feel the vibrations, you feel the vibrations, and this helps people learn in a different way, a more realistic way. So how did I investigate the brain and motion? Well, to go back to my simplified diagram is, well, the brain and motion I decided had two inputs, vision and vestibular, that's body cues. And I wanted to find out if I tell someone they're moving left, what does the brain do? How does the brain interpret it? And what will they say? So if I only move someone slightly to the left, will they always say left? Will they always say right? Is there an equation or a model or statistics that I can use to describe this? So what we see here is a very simplified top-down schematic. So this is meant to be someone sitting, and you're looking at their head, and they see the little nose and they're narrow. And what we can do is, in virtuality, we can separate this bits of information. We can separate the body cue is saying left, but the scene is saying right. So you can even have conflicts. And so what would happen is the person would be moved along in a diagonal. And sometimes the diagonal would be very straight. So it'd be very hard, because we'd ask them, did you move left or right? And they go, oh, that felt straight ahead, left or right. We'd force them to respond. So what we knew was, one, the direction we moved them, and two, what they said. And sometimes people would go, obviously, no, if I move them straight left, they'd always say left. If I move them straight right, they'd always say right. But if I move them slightly left or slightly right, we'd have some uncertainty. And so so this is a sigmoid function or a logistic function. This is very popular so this function, which is on the x-axis, is the angle I move someone. On the y-axis is the likelihood of them saying right. So on the far side, they'll always say right if they're moved like 10 degrees to the right. If they're on the left side, they'll always say left. And the dotted line is my prediction. Now, this logistic regression here is to help describe, this is what the brain is doing. It takes in information and it sums it up, and we're able to make a prediction about what people would say that observed this. This same equation is used all the time in machine learning. This is how you can predict, is someone going to like something or not like something? Same equation, different inputs. So these were a series of studies I've included. You can have a look on my website or wherever on a list of studies about this with myself and my collaborators. But the take-home message was, using statistics and data analysis and a bit of mathematics, we're able to model how the brain combines information for self-motion, for how we move. This exact same model has been applied to how we look and hear, to how we combine sound and vision, or how we combine touch and sound. and we can make predictions. And actually, we understand some of the computations the brain does. But this is very important. The model doesn't work all the time. And that's so important with statistics and data analytics. You want to make a good model, but not a perfect model. In the end, you want a great model, but a good model is fine. This model breaks down for when you're younger, because actually when you're younger, you don't use the information the same. And when you're older, you use them in a different way as well. And that's important, because then we can actually say, at what point are people using them the way we think they should? And what points are they breaking away from that? So this led me to kind of bigger question. There, I just had someone saying left or right. But really what I wanted to look at was different areas of the brain and look at how the brain processes things. And this brought in something called mobile brain imaging, or using EEG, electroencephalography, while walking. So what we had here was we were recording people's brains while walking. So we could look at, we knew some input, we were getting to do something. We were to look at how their senses responded, how their motor, their movement responded, and how they made decisions responded. And we're able to look at their button presses, which is like the first bit, but we're also able to look at them stepping in place. So it's a much bigger thing. So we need a lot more data. And so to look at more data, we use EEG, electroencephalography. This here is one of the first recordings of EEG back in 1900s. And what EEG is, it's the signals of the brain. It's electrical signals of the brain. Back in the day, they would only record 1 or 2. This is used in hospital all the time to help diagnose epilepsy, for example. But you can also use it to understand how the brain works. This looks like a swimming cap, but it's a very expensive swimming cap, because every single one of those wires is recording a bit of the brain. It sits on top of your, like a swim cap. It's non-invasive. It's very straightforward. Every single one of those is like a microphone, amplifying the sound of your brain, or the electrical sound of your brain. So what I got them to do is something called a response inhibition task. They'd press a button if they saw red. They press a button if they saw a different color. But if they saw the same color, they wouldn't press a button. So what happens is you have two things going on. You're clicking a button while you're walking, so it's like you're paying attention, but you have to stop. Like when you're walking up to a set of lights and you need to stop before walking on the road. It's response inhibition. You inhibit your response. You keep doing things, but you need to stop, and that's very important. So I looked at this when people were sitting and walking, in young people and old people. So the behavior, it's a bit less complicated than before. This is just means and standard deviations, which are the bedrock of statistics. And what we're able to look at people's reaction times, how fast they're doing it. So black is walking, red is walking and sitting. So what we have here is reaction times change while walking. Actually, older people got a bit faster when walking, which was funny. But stride time. So that shows that younger people changed how they walked when they were doing the task and when they weren't doing the task, because that makes sense. I walk slower if I'm texting and walking. I'll still walk into a pole every once in a while, but I will change how I walk. So what do we have with the EEG? So when we're recording all of the EEGs, what we have is what we have along here is time, and along the Y, on the up down, each of those is an electrode recording. So each of those is the electrical signal of that area of the scalp. So in theory, it's a bit of brain. So what we have here is we're recording the brain for a long period of time, but more importantly, we know what's happening. We know that that was a button press, no button press, button press, button press, button press, no button press. And therefore, we have repetitions that we can look at. So we're not looking at just a one-off event. We have to do a lot of these. This takes many, many hours to do on a participant to get their data. But when we get all this data, we can start actually looking at what parts of the brain are doing what during different parts of the process. So what parts of the brain are being used between clicking the button and not clicking the button? What parts of the brain are being used when you first see the square? So I'm just going to simplify our lives and only look across one very precise area at the back of the head, around the bald spot. So what happens is we have hours of data, but we slice it down to a few milliseconds, to almost 1 second of data, because that's how fast our brain is working. So what we have here is 0 is when they saw the thing. So after that, the first thing is that their brain sees something. So that's our sensory. A bit after that, there's this thing like an automatic area. It's between sensing and responding. It's when your brain kind of go, oh, something's happening, maybe I should be doing something, but you're not quite there yet, but your brain's doing something. Our brain's always doing something. We don't know it sometimes. And then we have the last part, which is decision. Yeah. So we're able to look at these up-down waveforms using different filtering, different tools, and compare them between when people are sitting and when people are walking. And what we saw with the younger people is, and this makes sense, is that this area that I'm calling the automatic time period, it got less, which made sense because actually that automatic stuff probably is being used to control walking. So they don't want to suddenly stop walking when they see something. They just want to use it. They say, okay, don't use that resource. While decision making is changed a bit, it's shifted, but not hugely. So what made sense was, what we saw was young people, they knew that they should weigh up. Actually, when I'm walking and doing something, maybe I should use less of the automatic stuff. I should keep that for walking. I should weigh it up like a balancing act. But older people who are already, now they're very healthy older people, but it's, it's walking on a treadmill and things. They already were at the maximum of their automatic resources. They didn't have that extra benefit of being younger, having a global network that worked better. So that meant that, so the top line there, that's the young people. The line below is the older people. Older people didn't change their walking strategy. They probably can't walk slower than that if they wanted to. They'd be stopping. And therefore, they had no extra resources. Now, this was fascinating because actually it showed that younger people are using different brain resources, while older people didn't have those extra resources to control walking. And we can extrapolate from that. We can interpolate from that to say that actually older people were more at risk, not because they're worse at the task or whatever. It's because those extra resources that younger people have weren't there in the older. So to analyze all that EEG data required a lot of data analytics. There's a lot of filtering. There's a bit of machine learning in it. There's a lot of statistics. And it's always at the very end. I can show you data, but the statistics tell me what is actually happening with the data. It can tell me if two data sets are different. It can interpret. So that's so important. And when a particularly complex data set that has millions of data points, gigabyte upon gigabyte of data for each person, you need good data analytics and statistical tools to reduce it. Now, as I said, the younger adults, they changed how they walked. The older adults didn't. And that change how the younger adult walked was reflected in how their brain processes the information. The older adults had less of this flexibility. And therefore, it's no surprise that actually walking is difficult. It's so easy to think walking is automatic, but it's not. The same resources that we need to say, oh, red light, green light, are the same resources that you're using for walking. So in a very cluttered environment that has a lot of stuff going on, that could be very complicated for an older person. And once again, there's a link to my website that has videos on this and other things, and there's a selection of some of the papers I worked on this area on the right. So Nolan, DeSantis, and Malcolm. So now, I talked a lot about the data analytics and statistics, but where does the mathematics come in? Well, mathematics is used in many different ways. It's the underpinning of statistics. It's the underpinning of data analytics, AI or machine learning or however you want to call it. But also mathematics is something else to itself. Mathematics can be used to make models, different kinds of models. There's statistical models, but there's also models to help understand how the brain works, for example. here is some work I've been doing, trying to describe how the brain, and I'm going to use the word population, how two population of neurons, so our brain is made up of billions of neurons, and what happens, there's a population in there that likes leftward movement, and there's a population that likes rightward movement, so L and R. And I have to describe how they talk to each other, how they interact with each other. And on the right, bottom right, there are the two equations that describe it. What you see there in the pictures are different modeling output that actually are the same as behavior. So I can show you a paper making someone distinguish between left and right, like I did earlier. And I can make data that looks exactly like that data. I can model that data. Why that's so important is, if I can model how someone does something, then I can actually change my model to see how it impacts the response. And that can inform you. So for example, if you have a motor movement disorder like Parkinson's, is it something that's sensory that's wrong, or is it just a motor delay? I can build a model that will help distinguish between those two, because a lot of these experiments that I do to gather this data are very long and time consuming, and therefore they're very difficult to run on different populations, different people. So if I can make models, I can make predictions. Now reduce the requirement to work on, do these experiments, but also make predictions. And as I said at the very beginning, that simple model I had to describe how vision and vestibular came together, it works really well for healthy adults, but it breaks for older adults and younger children. And while, of course, you're going, that's a failure. No, it's success, because I understand why it breaks and I can start thinking about ways of helping it. Because if you know why something breaks, then you can fix it. If you don't know why something breaks, you can't fix it. Now, more recently, and is actually in our master's in applied maths, one of our students was looking at these equations. These are mathematical models for pandemics. These equations, so I quickly go back and forth, they might not look identical to the equations there on the right, but they are very similar. These same equations, while modeling very different things, actually a lot of the logic is the same. And so what we have here is a model about infection, recovery, and death, and predicting how a disease happens. Now, there are all these numbers that are in these equations. We don't know what these numbers are. Most recently, we've all talked about this R0. We want the infection rate to be down to 0. Who finds out that data? The mathematicians make the models. The data analytics people find the numbers. You work in tandem with each other. These equations are well known, but we don't know what the numbers for the equations are. So you have to work together. For example, in my own work, well, it's not even work, I recently go around to some primary schools to talk about mathematics. And one of the models I use, which once again, you might not believe it, but these models here for pandemics are the same models that I use to describe how we could reintroduce wolves into Ireland and how actually it could be beneficial to the deer population. These same models can tell you what prediction is. Now, my prediction can be wrong because my numbers are wrong, but I need someone to get my numbers. And also maybe it can help decide how many wolves can come in. And more recently, of course, with the R0 is deciding which phase we are. We need data people to help interpret, to analyze data, to help drive what R0 is. Mathematicians were needed to actually describe the models, but data people are the people who finally get to their R0. Mathematics, statistics, and data analytics all work hand in hand. You don't have to be excellent at any of them, but each of them work together. You can be very good at one of them, and that's good enough. Data analytics can be used to develop models to describe complex processes from the brain to pandemics to ecology. And that helps us understand and model things. So statistics, data analysis, machine learning, AI, whatever you want to call it, and mathematics are supremely versatile. I am not a neuroscientist. I've learned a lot about neuroscience, but the reason why I was useful is because I could understand the data. I am not an optometrist, but the reason I'm useful is because I work with optometry. And I don't know robotics, but the reason I was useful, I was help understand the mathematics of robots. The role of a statistician or a data analyst or a mathematician sits in between worlds almost. They need to be able to talk to different people, to take in their data and to interpret it appropriately. Here at TU Dublin, specifically in the School of Maths, but computer science have it as well, we have a CPD in data analysis for professionals, which is Introduction to Data Analysis, analyzing using OR. We have a higher diploma in applied statistics. And then in the more mathematical side, we have an MSc in applied maths and an MSc in mathematical physics, where you can get strong underpinnings. While they sound very specific, they're supremely applicable to the rest of the world. And I'd like to thank you for listening. And all my work that I present here was done in collaboration with many people. I am just a cog in this work with my tool of stats, data analysis, and mathematics. Thank you.
Thank you, John. That was very interesting. Lots of valuable information there, I'm sure, for everybody who was watching. That was very valuable, and it was great to see it related back to so many different disciplines there. So we'd like to thank you for being our last speaker today. And we'd like to thank everybody for coming on and taking part in our event today. Thank you very much. Bye-bye.
Bye.